Hey, Stan, I want to welcome everyone to Math for the Impatient. We're here for the latest episode. And in today's episode, we are going to talk about random number generators, which is an incredibly important part of blockchain. So I think the first questions that I've got is, what exactly is a random number generator, and why are random number generators so important for blockchains?
Yeah, that's a great question, Marcos. And turns out that like a random number generator has very interesting, mathematical and physical properties. It just comes to the question, what is a random number? And turns out that, the simplest example, if you want someone to go to buy a coffee to a Starbucks, there are two guys, and they decide which one goes to Starbucks. They flip the coin. And when you flip the coin, what happens? You like throw the coin in the air, it like flips several times, and then it either lands on one side and on another side. Turns out that this is a pretty good random number generator, and because there is different air velocity, you can flip it in different ways. It can go up and down. Turns out that in physics, random numbers are really easy to generate, especially having that in quantum physics, what people found out is that there's really no fate or no deterministic evolution of a physical system. There's always lots of randomness. And some of this randomness is coming from quantum mechanics. Some of this is coming from chaos. So in physics, basically, there's lots of randomness. If you want to flip a coin, you just flip it, and one guy goes to Starbucks, and it actually can be done pretty fair. Turns out in computer science, it's much harder to have a random number. It's just because there's no randomness in computer science. You have a computer program, the program is supposed to always do whatever you tell the program to do. So how do you actually do randomness? So randomness in computer science is much harder to achieve than randomness in physics. But we at Scale live in the world of computer science. Our software is actually programs. So randomness is tough. But it's not only tough, but it's also really important for things like games, for instance, right? Like you don't want to play a game which would present you the same things all the time. So you need some type of randomness in a game. And then if you have a competitive game, you want this randomness to be fair. So you want all of the players to be treated fairly. And then if your game is a blockchain game, it's even more important because people actually can win tokens or NFTs in a game. And the game has to be random, has to present different random things to the users, but also has to be fair. So the randomness should not be predictable by any of the parties. So in this example, you and me are playing some game on a blockchain. And if I can control the random number generator, I will be able to predict what's going to happen in the game in the future and react. And it will actually provide me a much easier way to win against you. So if both of you are playing a game, we need to have a source of randomness that both of us trust. And if there are 100 people playing the game, you have to have the source of randomness that 100 people trust. And it should not provide an advantage to any particular player in the game. So super important for blockchain, in particular for blockchain games, to have a great random number generator.
Cool, awesome. So I think the next logical question here is, obviously this takes into account blockchain. Ethereum is what we're focused on. So what are some of the problems with the current Ethereum random number generators?
So yeah, that's a great question. Question is, if you have a game and the game is played on the Ethereum network, where does the randomness come from? Turns out there's only one random source, which everyone uses. And as I will explain in the future, it's not really random. So the randomness that everyone uses on Ethereum is the actual block. So there are lots of transactions in the block, and basically you take all of these transactions and create like a fingerprint of all of them. And so the transactions itself in the block, the way the block is structured, is actually the source of randomness, which basically means that whoever controls the block, how the block is structured, can actually predict the randomness. So which means that if you and me are not miners and an Ethereum block comes out, the new block, none of us can predict what's going to be inside the block, but the miner can actually predict. So if we are playing a game and the miner is playing the game, the miner can actually predict randomness and can always win against the two of us. So the only source of randomness that people use in Ethereum is the actual block, the structure of the block. It does look random, but it's not actually random because it's produced by the miner. So when the miner actually proposes a block, the miner knows for sure what the randomness is. And if the miner at the same time is the player in a game, the miner can win. So there is this important problem on Ethereum, lack of fairness. You can't really create a fair game on Ethereum. You can't also create a fair lottery. Or casino. I'm personally not a big fan of casinos or lotteries, but still, if you want to have a casino on Ethereum or lottery, if you want to flip a coin, there's really no way currently to do it in a fair way that no one controls.
So that leads to the last question, which is incredibly obvious because we're Scale, and this is going to be one of the things that we're thinking about. How does Scale's random number generator solve this problem?
Right, that's a really interesting question. And the way we designed the random number generator was that people first just were coming to us and saying, can you guys provide us a strong number generator? Because we want to do games. Actually, there's another interesting, important use of random number generators, NFTs. If you want to have lots of different NFTs, you also need to have random numbers. So NFTs are also kind of random, especially if you have many of them and generate the whole family of NFTs. So people are coming to us and saying, give us this random number generator. And it's actually a very complex mathematical problem. How do you flip a coin in computer science? And how do you make it in such a way that not a particular scale validator can control it? Because if a single scale node or a single scale validator could control the random numberness, then this particular entity or person could just play the game and win. And having that in this world, blockchain world, games actually have pretty substantial monetary value. This person could actually make money. So we need to have a random number generator which is random and does not actually depend on any particular node or any particular validator in Scale network. And it turns out that there is only one single mathematical algorithm known in the entire universe that, having a set of a large number of users or nodes, can generate a random number in a cooperative way, in such that not a single participant, not a single node controls the number. So, like there are like 16 guys, and each of these 16 guys does something, and then I kind of glued it together, and there's a random number, but none of them as a single entity can control what the result is going to be, and none of them can actually influence in a deterministic way the result. So you cook up your thing, I cook up my thing, other guys cook up their own things, and when the things get glued together, magically there is this random number, but none of us can actually know what the number will be because it actually includes entropy and randomness from all of the people. And only when this entire thing is glued together, you get the random number. So it's a collectively derived random number, or what is mathematically called common coin. The reason what it's called a common coin is because it's a coin flip which is common to a group of people. It's not me flipping the coin or you flipping a coin. It's somehow we do all of this jungling, and then suddenly, magically, you have this random number. So the only algorithm known in mathematics that implements and provides this common coin is called BLS signatures. So a BLS signature, something that we discussed already on this series, it's a group signature of many participants, but it's also looking pretty random, and it's actually the only known in the universe source of this group randomness. But because, as we discussed in our previous series, Scale blocks are already signed by BLS signature of 11 out of 16 nodes, we actually have this randomness for free, almost, because our block is already signed by BLS signature, and the BLS signature of the block is actually the random number, which is used by the network. And on every block, this random number is changing. And what we are doing in Scale Release 2, we are making this random number available through Solidity programming language, through EVM. So you, as a developer programming Solidity, you'll just have a very simple call. You'll say, get me a random number, and it will give you a random number. And then you can use this random number to create your game. So maybe some bots in your game go this way, some go that way. Whatever the game is, the actual landscape of the game, everything can be randomly generated. And this random number is unpredictable. We can prove to each of the players of the game that they are actually treated fairly. And we can prove to them that none of Scale nodes can influence this random number. So this becomes really, really strong mathematical statement. That's why we hope that starting from Scale Release 2, which is hopefully going to be coming soon, lots of games will be able to use these random numbers as a very basic, important block of the game. And users that play the game will know that the random number does not depend on any particular personal entity. It's really fair. So that's really how the random number generator works.
That's very cool. I think it's worth, if you have just, if we could encapsulate maybe in just a few minutes, what are the basics of a BLS signature? I know we went over it in another video, and I'll add that in the notes, but worth doing like a minute or two on that just so people remember.
Yeah, let's do it again, because I think the previous video was done like quite a long time ago. So BLS signature is an extension of a regular digital signature. Pretty much everyone has used a regular digital signature. You have a key, you sign some document. There are now software products that do digital signatures. Many governments move to digital signatures. So regular digital signature, people now used to it. You have a PDF document, you have your private key, no one knows. You do this magic thing, you click the button, and then there's this additional thing added to your PDF document. It's a series of bytes, basically. That's your signature. People know what digital signatures are. A BLS signature is a group signature. It's a very cool object that allows not only a single person to sign, but a group of people to sign. That's why it's also called sometimes threshold signature. It actually signifies the fact that not a single person agreed to this particular document, but a collective, a number of people agreed. And at Scale, a default number of nodes in a blockchain is 16, so we typically use supermajority 11 out of 16 signatures, which means that for a particular statement to be truthful in our network, 11 out of 16 nodes need to sign the statement. So the way things go, let's say you want to have a collective signature for a particular statement. And the simpler thing is a block in the Scale network. What is the true block? What the user needs to know, is this block the real thing that has been generated by Scale network, or something bad? So the way for the user to know that a particular block in the blockchain has been generated correctly by Scale network, each block has the signature, the threshold signature of 11 out of 16 nodes. And the way this signature is done is that each of the 16 nodes has a secret key. So if they want to sign a block, each of them is using her secret key to create this piece of a signature. It's like a jigsaw. It's not the entire signature, just a piece of it. And once 11 out of 16 nodes, no matter which 11, have these 11 jigsaw pieces, any of these 11 jigsaw pieces can be glued together, and magically you can imagine like you being a magician, right? And magically you have these 11 pieces, and then something happens, and then instead of 11 pieces, you have one piece, and it's a BLS signature. And this threshold signature can be verified independently, no matter which 11 nodes signed. The fact that you have this mathematical object, it actually means that 11 out of things signed, and magically, no matter which of them signed, which keys are used, which combination, the result is going to be the same. So a threshold signature or BLS signature is an extension of the notion that we have already in our world, which is a digital signature. But a digital signature is a signature of a single person, and a threshold signature is a signature of a group. It means that a group of entities voted for a particular statement. So that's the threshold signature, and we have it in each scale block has this signature. And as already described, the interesting fact is that this threshold signature is also providing a solution for a very different problem in mathematics, which is called the common coin. It's a commonly generated object which looks random, which is random, and which can't be controlled by any of a single party. So that's really means that the BLS mathematics, the mathematics which has been with us for the last like 100 years almost, is actually creating so many good things for the blockchain. It provides us the threshold signature, provides us the source of randomness, and as we discussed in one of the previous series, has interesting story. There was this mathematician in France that actually got into jail, and then in jail he actually created this mathematical object which was called while pairing, and which had absolutely no use for like almost more than 50 years. But suddenly in 2000, Dan Bonnet and two other people were able to use this mathematical object that Andre Weil created in 1948 to create this entire mathematical field of BLS, of threshold signatures, of random number generation. And without this particular mathematical object, none of this would be possible. And we don't know anything else in mathematics that can provide this. So this, this particular branch of mathematics turned out to be incredibly successful. And it's like something that in 1948, people would probably think as totally unusable and abstract and mathematical and having no relationship to the real life. Suddenly we have this used now by many people.
Very cool. Awesome. Well, thanks again, Stan. That's this week's episode of Mathematics for the Impatient. You can check down below in the notes and you'll see our Twitter account, our Telegram. Please join the different groups, like, reshare, all those great things. Thanks again. Bye, Stan.
Bye, Marcus.